This video is a quick review of some of the basic things you should have learned in Intro to Statistics, and there's a companion video about ANOVA and chi-squared that comes after it. So this should be considered sort of a review and a supplement to what you know. You can use them to review Stat 202 or to preview Stat 202, but if you know most of this material, it means you're probably okay to go on to an upper level stats course. That's my opinion. Take that with a grain of salt. And some of the graphics I just grabbed off the web. The ones that I thought were non-standard I tried to reference. Things that looked like boilerplate I didn't bother referencing. Okay, so why do you want to do statistics? Well, first of all, you want to answer questions about the real world, sometimes in science, sometimes social science, just because you want to know how the universe works, or how the world works, or how the thing you're studying works. You might have a very specific question like in business or production or finance because you have a very specific goal or financial incentive. Or you might want to just explore the theory behind statistics as its own objective. Maybe you want to improve the practice of statistics, or you want a better idea of how to analyze your particular pile of data. There's all sorts of reasons. But it all starts with data, except maybe the theoretical study, but you're still studying the idea that there would be data behind your theory. You might find a pile of data or collect it yourself. You should really know where the data came from. That makes a huge difference. Your goals should be clear. You should know the setting. You should know how accurate your results need to be for your purposes. In many math or stat courses, we pose questions to students which are considered pure and other questions which are considered real. Of the real world questions in math and stat courses, some are actually real, but a lot of them are just completely bogus, made up crazy stuff that would never really exist. So I consider these to be three separate categories of questions in any math or stats course: pure, fake real, and real real. So this is a pedagogical construction. The more traditional view is that students would be taught a more generalized theoretical material in the classroom, and then when they graduated they'd be able to match their own real world problems onto the theory. The newer tradition encourages having students practice doing this mapping while they're still studying the theory to make sure they can match up the theory to the appropriate situations. That's not to say that people didn't used to use data sets in class. Of course they did, but I think there's more emphasis nowadays on having real data. And that makes a lot of sense because we have computers, and there's a lot of other reasons why we do that. But this just is a sort of pointing out a trend in pedagogy. Okay, so beginners and experts all start by asking, where is this data? This pile of data I have, what is the middle? Is this thing skewed right or left, or is it symmetric? It could have any distribution, but the most common ones we look at in introductory stats are normally distributed or skewed right or left. We want to know where the upper and lower ends are, and that gives us a range or domain depending on what you're doing with it. You compare different ranges. So for example, here this math paper has a range of, you can say the range is between 30 and 80, or you can subtract and say 80 minus 30 is 50, so that range is 50, whereas this range is 80. Those are two different ways of thinking about the range. How clustered together are the data elements? Okay, so we think in terms of a normal distribution, but in two-dimensional data we may think of clusters, like here's a green cluster, a blue cluster, a red cluster, or we could think of the whole pile of data together as being clustered in some way. This is another way of thinking of clustering. Here's like a one-dimensional set of data, and it's clustered here, but in this set it's in three piles. So these clustering patterns are different. Some basic tools we have to find mean, median, mode, interquartile range, standard deviation. We use box plots, stem and leaf plots. We use histograms, bar plots, scatter plots, basic tools. Here's some more things. Here's the scatter plot with some lines going through it. It's a couple, maybe a line of best fit on this data and a line of best fit on this other cluster of data, and it kind of connected somehow. Some basic tools we have. Scatter plots quickly lead to best fit lines and correlation. Any type of curve can be fit to data if it's displayed as points in a plane. Like you can do a quadratic or square root or exponential or logarithm, anything you want, but mostly we start with a line and we go from there. It's the most common thing we do. This set of dots has no linear correlation whatsoever, and thinking of linear correlations, if your points lie exactly on a line, in this case this is a +1 correlation or very close to it. This is very close to -1, and then this will be positive, but it's going to be maybe like 0.5 or something. And this is going to be negative, and it's going to be closer to 0 than to -1. This is going to be closer to -1 than this one, and so forth. Okay, some other basic tools we have. We have these side-by-side box plots. It's very common, so you can just view the interquartile range. So this is Q1, Q2, sorry, yeah, Q1, Q2, Q3. There we go. Another thing. What is the difference between a bar chart and a histogram? I really don't care about this artistic distinction, but the artistic distinction is there to indicate that there's a more important concept you do need to understand. We put gaps in between the bars. These are not discrete bins, even though we've broken the data up into bins. Okay, so we usually do not use gaps when indicating that the data underlying the plot is actually continuous, and we usually do use gaps to indicate that these are distinct categories. Okay, so there's again, I don't really care about the artistry, but I do care that my students understand the difference between binned data and continuous underlying data, which has been binned. So those are two different concepts. Okay, so why the normal curve? All right, there's two things I want to say. One is like it's really, really important, and the other one is like, it's not that important. They're both kind of true. And why is it really important? Well, when you repeatedly sample any population, you always end up with normally shaped data if you do it correctly. But the underlying population doesn't have to be normal. It could be any shape you want. And that's the thing. Your normal shape of your underlying data is not, excuse me, it's not going to be normal. Okay, so we kind of pretend like the world is built on these normal distributions, but it really isn't. It's just repeated sampling. It's a little bit artificial. That's a construct we've created. We've created normally distributed examination scores. Okay, so for example, if you ask 100 people to use a 1 to 7 scale to rank something like 1,000 times, this is what you expect. This isn't actually what you usually get. It's usually skewed up a little bit. But let's just pretend. Let's just pretend this is what it looks like. Okay. If you have several different classrooms and they all give the same exam, the exam scores for one classroom might have any distribution you like, any old distribution. But let's say you have thousands of classrooms. Let's say you think about all the different classrooms in the United States, all the high schools that are giving the AP Calculus exam or the AP Statistics exam or whatever. And you take each classroom and you take the average score for students. Classrooms themselves don't have a normal distribution, if that makes any sense. If you plot classroom averages for thousands of classrooms, that should be normally distributed. Here's another example. If you have one coin or a die, or a spinner, for example, this could be really unfair. So it could be a 70-30 split, let's just say. Now, if you take a spinner on here and you say 70-30 as your chances, whereas in this case, let's say 30% chance of success. And then if you spin it 10 times, you're most likely to get 3 successes. And let's see, here's this tall bar at the number 3, and that's what we expect. Okay, this doesn't really look normally distributed yet. It's starting to get there, but it's not. You could have anywhere between 0 and 10. So these two bars are not showing, but they're really there. So you could have between 0 and 10 successes. But what if you choose, instead of 10, you chose 1,000? This, you're going to have expected value of 300, and fall, the two edges look like they have a different shape. But here, the rise and the fall look like they're about the same. Okay, so most underlying distributions, even ones that look bell-like, are not necessarily normal. We make up lots of questions for students which presume a normally distributed population, and this usually for pedagogical simplicity. However, many statistical tools will do well with which sets of data, so that's just sort of a warning. Okay, so we're jumping in with both feet here. I told you I'm kind of reviewing all of Intro to Stats in one set of slides. So basic stats courses pause to discuss probability before they go into a lot of these other issues where we're going to do hypothesis testing and things like that. We talk about probability first because in probability we control everything. It's completely theoretical, and we really ought to at least understand the theoretical limits of what we're trying to accomplish before we add in the layers of complexity that reality brings. So for introductory statistics, we make lots of completely unreasonable assumptions, and that's okay because we need to start somewhere. So ironically, for the simplest case, we add a lot of conditions. For example, we have this, dice, coins, and spinners are the most common things we study in probability because they're completely predictable and they, for the most part, behave the way we expect them to behave. We limit the concerns we have only to theory, and we don't have to worry about, oh well, maybe our die is not fair. Because most of the dice that you use are reasonably fair. Most of the coins you use will flip pretty well. Most of the spinners will spin fairly well. So when we construct these pure worlds, we focus only on the sampling effects, and we ignore all the other possible issues which we have to deal with in real life. Sampling effects alone are enough of a problem that when we remove all other issues, they still loom large to interfere with our ability to make statements about our data, or based on our data. Okay, what about two-way tables? Let's compare gender to right and left-handedness. We create pure questions using data with two-way tables. So we can classify exercises as real world, even if they're pure. We can talk about conditional probabilities using two-way tables. Two-way tables are really common. I picked this one off the internet because this is really intriguing to me. This is saying that if your eye color and your hair color were not correlated at all, this is what you'd expect. So you take, your percentage of black, brown, red, and blonde hair, and you split this up. So let me see, how many blocks are there? 5, 6, 7, 8, 9. About, I don't know. So each block is about 4%, 16, 17. So this is guessing that about 17% of the people have black hair. And this is saying that about 12% of the people have green eyes. And if that were true, you would expect like a certain percentage of the people to have like black hair and green eyes because you can multiply these probabilities together. That's not the way it actually works. But that's the theory, right? If two things were unrelated, you should be able to multiply their probabilities together and guess what the expected value will be. Okay, what is p-value? This is something that we can only understand in theory. Okay, so we need to understand what the null hypothesis is. The p-value is the chance that you obtain a result as extreme as the one you measured if the null hypothesis is true. We also need to talk about the one-tail and the two-tail case. What's the difference? Why would you use one-tail versus two-tail? What are the most common question types in the real world? Okay, let's answer. Okay, what is the proportion of U.S. households having Christmas trees over the holidays? Or that would be a proportion question. What is the average value of a parameter? How many computers does the average teenager own? How do two populations differ? Do males or females spend more hours per day talking? Can we change or improve something by our interference? So, for example, can we increase test scores by studying? Those are really common question prototypes, and these all have to do with hypothesis testing in one way or another. We also want to know, is something changing over time? We want to compare several groups for proportionality. We often use two-way tables and chi-square for that. We often want to compare several groups' mean values, and then we often use ANOVA, and then we add along something like Tukey test to that, so that we can tell which groups are higher or lower than which other groups. So now we want to know what p-value means. So let's back up for a minute. What situation got us to the point of calculating a p-value? Well, we were probably just asking one of these types of questions. One of these bulleted questions is probably what led us to asking a p-value, asking us to calculate a p-value. And we wish to know how reliable our results are. We need to quantify uncertainty and put error bounds on things, give margin of error, and possibly certainty measurements. So I want you to think about this generic process before you sort of tie it into what you've done in statistics class before. So start with this generic process. I have an idea of what I think reality might be. Maybe I think that 30% of households use live trees over Christmas. I don't know. I'm just making this up, okay? But I come up with some kind of hypothesis. I can simulate that on a computer hundreds of thousands of times to create fake samples I would expect to get if my assumptions were correct. So for example, if I think each household has a 30% chance of purchasing a live tree, I can simulate a group of 10, a survey. I can take a survey of 10 or 20 or 50, and whatever I choose to be my sample size, I can do this over and over and over again, and I can just simulate this. This is something that's known theoretically, but let's say we didn't know it theoretically. We could still simulate something even if we don't fully understand the mechanisms behind it, because if we start with assumptions that we can write down and we can simulate it, then what we do is then we go out and take an actual survey and see where that survey lies on our created distribution that we simulated, okay? If it's a known theoretical problem, I can use mathematical formulas which were already provided in the field. For this level of study, though, we focus mostly on known distributions. So the thing is, you can create any simulated distribution you want, but when you're in Intro to Stats, we stick with the tried and the true, and rather than simulating things, we just look stuff up in books. Okay? But it all came from the beginning saying, hey, we'd like to do this experiment. So even for unknown distribution, repeated samples are going to go where? Aha! Their means will form a normal distribution. Then you make a comparison. So for example, remember what we did before? We had, like, out of 1,000, we had each draw had a 30% chance of being red, or for each time we click the spinner, had a 30% chance of being, actually I think it was supposed to be green, I don't know, but it's a 30% chance of success. And so this is what this bar graph looks like. Here's all the likely samples I would expect to have gotten. So I simulate this. And then let's say I draw a sample. And I draw 320 red balls out of 1,000, and I had believed that I had a 30% chance to begin with of drawing, making a success each time. So is this 320 counter evidence that maybe I had the wrong count, that maybe it isn't 300 red balls, maybe it's some other number? Is that unusual? So given that we know nothing else, but just looking at this plot, here's like, if your null hypothesis is true, if 300 is the true number of successes out of 1,000, and you do this experiment 1,000 times, and this is the expected the expected draws. 320 is around here. It doesn't look that unusual. It's not far, far, far in the tail. It's not right in the middle, but it's not too far off. So let's quantify this. See, in statistics, if you're like right in the middle, you don't have to be suspicious. If you're way in the tail, either tail, you're going to be suspicious. It's when you're kind of on the border, you're not really sure how suspicious you ought to be, then we crack out the numbers. Okay, so what is the p-value here? So what I'm going to do is I'm going to say, okay, this is StatCrunch. I pull out a binomial calculator. I say 1,000 different times. I'm going to run the experiment with a success of 0.3 for each of these n. And I want to say, what's the probability that I'm going to get an x that's 320 or greater? And I get 0.089, which is close to 0.09. So about 9%. But that's not entirely fair because it could just as easily be low as be high. And I want to know what's the probability of getting a value that extreme, not just that high. So I should probably multiply 9 by 2 and get 18. So it's about 18% chance of getting in one of these tails. So the p-value would be about 0.18, which is pretty high for a p-value. Okay, so it's about 18% likely that you'll have a value in one of those two tails, and so I don't think that it's very unlikely at all. And my other comment here is that I don't like one-tail tests because it artificially lowers your probability of getting in the tail. If you say, hey, what's the probability of getting in the right-hand tail, you're going to say 9%. And it might look like a smaller p-value, but it's not really fair because you're completely ignoring this other end of the distribution. There are some cases where it's justified, but when in doubt, use two tails. If you're at all unsure about whether you're in the right, just go for the conservative approach and just double that tail value, and then you'll have a more conservative p-value estimate. Okay, so it doesn't prove anything. You can't prove that you have 300 red balls in there, or that there's 320 red balls, or any such thing. You can say you are fairly sure the ratio is close to what you thought it was. That's pretty hazy. But unfortunately, that's the best you can do. What is the null hypothesis? Well, it's actually really boring. It's the boring default based on whatever your setting is. It's simply the claim that is being made. You can never prove it. You can only fail to reject it. Many authors gloss over this point, much to my own frustration. For my students, I ask them either reject the null hypothesis or fail to reject it. Don't say anything else. When the evidence is strong, you can claim to reject. You could still be wrong, but you should quantify your level of confidence. When there's no evidence against it, you can't discredit it. You could, again, still be wrong, and you should always quantify your level of confidence. Why can't you prove the null hypothesis? Okay, since so many people have trouble with this, I want to just stress this. I'm going to give a simple example. Let's say Alice claims population average is 95. Bob claims it's 98, Clyde claims it's 87, and Doris claims it's 101. Each of these four people have a different claim. So for each of them, they have a different null hypothesis. They take a sample and get the following results. All of them. They share their data. Even though they have different claims, they decided to share their data. Tell Bob, we can't prove you're wrong. We tell Clyde, we can't prove you're wrong. And Doris, we think you're wrong, but we could still be wrong. But we're actually going to officially say we think Doris is wrong. That may sound really, really sketchy because we're not actually saying anything. We're just sort of bounding we're bounding our uncertainty. We're saying that at this level of confidence, we're going to let A, B, and C go with their claims and say, hey, you can all say that, and Doris, you need to stop saying that. That's all we're saying. Who is right? Alice or Bob or Clyde could be right. Maybe none of them are right. Doris is probably wrong. But for sure, Alice, Bob, and Clyde cannot all be right at the same time. But just because we failed to reject all of them doesn't mean we're accepting any of them. We're not necessarily accepting, we're just saying we think Alice, Bob, and Clyde are fairly close and Doris isn't. That's all we're saying. Okay. Now what? What's this thing? Hopefully you remember the difference between the normal distribution and students' t distributions. It goes by different names, t distributions, student distributions, whatever you call it. It's this, as the degrees of freedom goes up, 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 your curves on your t distributions approach the standard normal curve. So by the time, let's say you have a sample size that's like 1,000, you're just going to use the standard normal distribution. But for smaller sample sizes, you're going to use different distributions, and you see they look very bell-like, but they're kind of like somebody sat on them. And the smaller your sample size is, the longer they got sat on, pretty much. Why do we use student tables? Student, by the way, is the name of the guy, Mr. Student, who wrote about these distributions. I think he worked for Guinness. So we should call him Mr. Guinness. But anyway, call him Mr. Student. The classic problem is where you go out and you collect data, you probably don't have gobs of data. You probably don't know the mean or standard deviation of the actual population, or you wouldn't be doing this. You really can't find out the standard deviation until you know the mean. So this is not a bad guess. This is the standard problem of you just go out and take a survey. Okay, you end up with a sample mean and what I call the so-called sample standard deviation. Okay, you get those values. And then what? What is this so-called sample standard deviation? Well, if you have a population, that population has a mean and a standard deviation. We don't know what it is. But from the sample, we have something called statistics. And from the sample, we have a sample mean and a so-called sample standard deviation. The reason I call it that is because what it really is this guy, this S, is an approximation to this sigma. I'm concerned because students say sample standard deviation and they think it's the standard deviation of the sample. It's not. So what it means is you've taken a sample, we're now going to calculate an estimator for sigma, and we're going to label it S. Okay? So that's why I call it the so-called sample standard deviation. Why does your calculator have a button for X bar and S and sigma, but it doesn't have a mean on it? Well, that's because if you actually have all the data and you stick it into your computer, maybe your whole population is only 10. Well, the way you calculate the mean for a population is exactly the same way as you calculate a mean for a sample. And so you don't need a separate button. These are calculated using the same exact process. But this actual standard deviation, if you have the entire data set, use a different process than if what you have is a sample which was drawn from a population. Use a different, slightly different process to create the estimator for sigma if what you have is a sample and not the entire data set. Okay? And that's why there's two different buttons on your calculator. Okay. If you're given a set of data on homework or an exam, if you're calculating the standard deviation, it's more than likely S is what you want. In order to find sigma, you need all the data, which you probably don't have, again, on a homework or an exam. If, however, I gave you like a data file and there's 10,000 items in there, then maybe you can find sigma. But in that case, sigma and S are very close, and then it doesn't really matter at that point. Okay? You can always just use students table when in doubt, because if you have a very large set of data, then your S calculation is going to be very close to sigma, and your normal table and your student table are going to be very close. So it never hurts to just use students when in doubt. In some contrived situations, normal distribution is fine. You can err on the side of caution by using students. One of the times when you can use the normal distribution is if you're taking a sample and looking for a proportion. You're just looking for yes, no, binary, yes, no, agree, disagree, that kind of thing. If you're asking that kind of survey, then you can use the normal distribution even though you may have a smallish sample size. Okay, so that's kind of an exception. If you are given a standard deviation, you might be looking at a sigma or an S, so read the question carefully. Simpson's paradox. You should know about Simpson's paradox. So if you have a set of data and there's an important breakdown of the data, like red dots and blue dots, you could say in the blue dots, the data are positively correlated between X and Y. And within the red dots, it's also positively correlated. However, if you don't make note of this color distinction, you may think the whole entire set is negatively correlated. And this is a really common problem. So Simpson's paradox leads directly to the concept of chi-square, or even ANOVA, things like that. Simpson's paradox is the odd result you can get that's backwards from reality because you didn't analyze your data in a meaningful way. You didn't split your data along a really important variable. Each group may have a meaningful and similar trend, but due to the groupings not being honored, the trend appears to be in the opposite direction. In order to verify that the trend is even real, we should be testing a two-way table in a chi-square sense. It kind of bothers me because usually introductory statistics books talk about Simpson's paradox and they don't talk about whether the results are even statistically meaningful. So that bothers me. So I try to look at both of these concepts at the same time, Simpson's paradox and chi-square. But I'm not going to talk about chi-square in this set of slides, but I have another set of slides that I want you to look at about chi-square and ANOVA. Introductory statistics students are often not expected to master these concepts, but it is covered in most AP Stats classes, for example. So those topics may or may not be covered in a basic statistics course. They're usually things that you study at the end of a basic statistics course or that they get skipped. But the chi-square concept really is important, or you can't really understand the Simpson's paradox very well. Okay, so hopefully you will go on and first take a break and then go watch the other set of slides.